Good morning, good afternoon, and good evening, wherever you are in the world. My name is Steve Lewis, and I'm a Senior Director of Risk Tech based here in the UK. Thank you very much for joining us, and welcome to this Risk Tech webinar, which is the fourth and last of Series 7. The subject of today's webinar is about ALARP assessment with a focus on offshore wind farms. And it includes a brief case study on boat landing inclined ladders. Hopefully we can provide some useful and practical insights for you. The webinar is going to take about an hour with around 45 minutes for the presentation, which would leave us 50 minutes for Q&A. We've muted everybody so that the sound won't be distorted by any background noise. If you'd like to ask questions, and we really do encourage you to ask questions, then please use the Q&A function. If you're not familiar with Zoom, you just put your cursor on the screen, drag it down the bottom, and the ribbon should come up at the bottom, and then just click on the these Q&A speech bubbles, type your answer in, type your question in, and we'll aim to cover as many of them as we can at the end of the session. Okay, I'd now like to briefly introduce Risk Tech. For those of you who don't know us, apologies to our regular participants. You've probably heard this a few hundred times before, but I'll be pretty quick. What we do is we help clients to manage health, safety, security, environmental and business risk, particularly in sectors where the impact of loss is high. We do that through 5 business lines: specialist risk and safety management consulting, online and classroom training and postgraduate education, resourcing, which really means providing associates to work at client locations, perhaps where they have a skill shortage or need to fill or short of resource. We also provide industrial and vendor inspections and assessments as part of asset integrity management, and we also undertake research and development in the field of risk and safety management. I'll now introduce our presenter today, Richard Tiffin. Richard is a principal engineer. He's based in our Warrington office in the UK. He's been working in the field of major accident hazards and environmental management across a range of high hazard sectors for over 22 years. Now, over the last 8 years, he's worked on delivering safety, health and environment management on a number of offshore wind farm projects. That's involved a variety of activities such as running workshops, undertaking assessments, and producing documentation, which including ALARP assessments to support the demonstration of safety. Okay, Richard, over to you.
Thank you, Steve. Hello and welcome to everybody joining this podcast, or webinar rather, which, as Steve has introduced, is about ALARP processes for offshore wind farms. And we're going to talk about that and outline a number of processes that are transferable and applicable in a range of circumstances. And I'm going to use an example from one of the projects I worked on extensively in the early part of my time at Risk Tech. And it was a contentious issue of whether or not to adopt an inclined boat landing. So I'll take you through the aims of the webinar, which is to look at SHE compliance across offshore wind farm projects, and the examples I'm going to use often cite UK regulations, but they are broadly transferable and are applicable to any situation worldwide and any project worldwide. I'm going to take you through some of the methods and techniques which can form part of that ALARP design process that have been used and tried successfully. And the object of these methods and techniques is to manage risks through design and to manage residual risks to as low as reasonably practicable, or ALARP, which is a term no doubt all of you are familiar with, but if not, raise a question and we can go into that at the end. So at the end, we're going to look at the case study, and then at the end, look at applying a sort of trimmed down version of the process to smaller problems and see how that looks. So I'm going to start by looking at what I mean by an ALARP design process, and as it applies to an offshore wind farm. As you know, offshore wind farms, even onshore wind farms, involve a range of assets and facilities. So we have wind turbines, we have an offshore substation platform, we have an onshore substation, typically linked to the offshore wind farm by underwater cables. And in this case, in this instance, where the wind farm, wind farms can be served by a service vessel offshore, but in this case, we're looking at one that's a little bit close to shore, so within about 20 kilometers of shore, and is serviced and accessed generally by fast crew transfer vessels for transfer of crew to maintain these assets. And those vessels operate out of a local harbour, and at the top of the screen you can also see a helicopter, signifying that there may be use of helicopters and also search and rescue helicopter operations supporting the operation. So if you're developing a wind farm and all of those assets, you could envisage having a standard that sets out the principles of ALARP and the techniques to be used to deliver it. And so this schematic really represents such a document, and it would have the same sort of iterative approach that that quality systems and management systems have, the plan, do, act type of loop, and it would define the underlying philosophies and the core principles of the ALARP for the project. And the procedure would also cover activities and how to implement those things, and also specify what sorts of documents might be produced as outputs of those activities. And so within UK law, there's a principle of prevention which sets out that developing a coherent overall prevention policy which covers technology, organisation of work, working conditions, social relationships, and the influence of factors related to the work environment is built into the regulations, and the ALARP process, or ALARP design process, is a good way of building a system which delivers on those aims and intentions, and thereby complying with the regulatory requirements, but also ultimately delivering a facility or facilities that are going to be safe, where they've passed through a process which ensures their safety. You can have confidence in that, and that there is underlying arguments and evidence, documented evidence, which supports that assertion. And so, so the ADP philosophy that drives a process based around 4 key principles, which I'm going to explain on subsequent slides. So the first is the adoption of good practice. The second is the principle of a hierarchy of hazard management. The third, management of uncertainty around an ALARP decision framework. And fourth core principle is around what is tolerable and acceptable risk. So let's look at the first of these, the good practice. So the HSE in 2001 published a document which defines what they mean by reducing risks to ALARP, and it can be found and downloaded for free off the HSE's website under reducing risks, protecting people, or often it's summarized to R2P2. And this document states that the starting point for ALARP should be an option which is known to be reasonably practicable, such as one which represents existing good practice, something that's been implemented, for example, in half of equivalent facilities might be something that you could call good practice. Any other option should be considered against that starting point to determine whether further risk reduction measures are reasonably practicable. So what we mean by good practice are legislation and approved codes of practice, which may include requirements, but equally often they are recommendations or processes which would determine things that represent good practice. Then you might have industry guidance, which draws on industry experience for a particular sector. So, for example, in the wind farm, for a wind farm, G+ guidance for the wind industry in the UK is a perfect example, and there are documents around working at height and various things like that, and then international standards, which may be sort of ISO standards or EN, British EN standards on things like design of electrical equipment or design of work access equipment. So there's a whole raft of good practice, but it doesn't necessarily cover every specific situation which you're dealing with or necessarily represent the best ideal solution in your case. So starting from that point, further risk reduction options can be considered. And we sometimes call this process optioneering, but one of the great benefits of it is that it broadens out your view of what is possible or not, which can then be filtered back down to a list of what is preferable, what is represents good value in terms of cost versus risk reduction benefit, and may represent opportunities which hadn't previously been considered. So a great deal of benefits in widening out your risk reduction options at this stage and thinking broadly. The second core principle, which you'll all be familiar with, is built into most standards and a lot of regulations, and that is a hierarchy of risk reduction, where avoiding risk wherever possible is the ideal, or where it's not possible to avoid the risk and eliminate the risk altogether, engineering solutions are preferred over individual solutions, PPE, personal protective equipment, and or procedures and discipline at that individual level. So elimination. So there's a familiar saying or acronym ERIC-PD, which is cited in a number of sort of risk assessment processes, elimination, avoidance or reduction in terms of volume, inventory, or of hazardous substances, isolation, moving further away, enclosure, control, and then personal protective equipment and or discipline. So the level of effectiveness of these measures decreases as you work towards individual measures. Certain specific regulations, for instance, the work at height regulations in the UK, which I think have their equivalent in EU legislation, contain a hierarchy of risk reduction specific to the area of working at height, the risk of working at height. And so the most desirable in this case would be equipment which prevents a fall. And then moving on, work equipment which minimizes the height of a fall and the consequences of a fall if a fall cannot be possibility of a fall cannot be eliminated. And then next best would be to minimize the consequences of a fall, if not, being able to prevent a fall in the first place. And at the least desirable level would be work equipment which does neither. So an example, rather spurious example to illustrate this principle would be, for example, a stunt man wanting to perform for a film or whatever, or a circus act, whereby you want to, for effect, let's say, jump off a high building, and you don't want to minimize the height. You don't want to stop them falling in the first place because it's their job. You don't want to minimize that. Well, you can minimize the height, I suppose, to a certain degree, but the job requires you to fall a distance. But you most certainly would want to minimize the consequences of that fall. And it's also worth saying that to get to the point where they're going to jump off this building or bridge or whatever it may be, the principles of working at height would apply. So you would probably work to a solution where the stuntman would walk up a set of a staircase, if possible, or some kind of secure access, fixed permanent access or temporary access to a secure working platform from where they were going to access the point at which they were going to jump off and fall a distance. So at the top level, collective measures are preferred over personal measures. So you would ideally have a safe working platform which person cannot fall from, with a permanent fixed access which contains and prevents you from falling a distance. So a mobile elevatable work platform, for instance, a MUP or a mobile tower, or a fixed staircase leading to a barriered platform with handrails. At a personal level, if you, for instance, if that platform, like on a wind farm, the working platform has gates that need to be opened to facilitate lifting operations, for instance, you would want to ensure that personnel could not fall when those gates are open. So you're not, in that case, you're going to resort to individual protection that prevents a fall, so working in restraint of that sort. Then collective solutions at the next level might involve soft landing systems or nets at high level. Worse would be nets at lower level, but it would depend on practicality. And at a personal level, you would employ personal fall protection systems. So perhaps, for instance, on the boat landings, the self-retracting line type of fall arrest systems that are on fixed permanent ladders, or attachment of an energy absorbing lanyard to an anchor point, which would be attached at high level, so that if you did fall, you would the forces that you experience through your harness would be minimized so as not to injure you. Okay, so similar sort of things, soft landing systems, collective systems, and injury reduction systems like life jackets or inflating jackets might come in at personal level. They're less common, I guess, when you get down to this level. And examples where no protection is provided would be ladders, for instance, or minimal protection is provided. I mean, you could provide some protection if you put a ladder, but these sort of temporary movable access solutions are the least favoured, and collective versus personal equipment with trestles and guarding. So anyway, it's a bit of a sort of long slide, and I spent too much time on it, but that shows this hierarchy, which is an important core principle that we're applying. Next, uncertainty. Now, the example we're going to talk about is one where this was little used, and where uncertainty exists in a design, or where there's less guidance on a particular design, or it's a prototype, then you're moving across to the right in terms of the level of risk. There is also likely to be greater stakeholder influence from people who are going to be operating this equipment, contractors, and potentially regulators as well. So as you move to the right and greater uncertainty, then you move from good practice to engineering assessments of different levels through to a precautionary approach where you might say, well, we'll revert to existing practice rather than try out something new if the opportunity and the risk reduction benefit cannot be demonstrated sufficiently to persuade all parties. So the final core principle is that of tolerability of risk. And this diagram is taken from risk reduction, prevention of protection of people, R2P2, and sets out what the HSE consider to be tolerable risk or intolerable. So at the top, you've got the unacceptable region where risk cannot be justified except in extraordinary circumstances. And that boundary equates to risk of fatality of a worker of 1 in 1,000 per year. The bottom of the diagram represents what would be a broadly acceptable risk, where the risk is generally insignificant and the risk reduction would usually not be required, but still would put in place obvious and easy to implement measures to control risks further. And then between those two regions, then you have to reduce your risk as far as reasonably practicable to be able to accept that level of risk. And that's what the ALARP process is all about, is moving from higher up on the risk triangle, the red area, as far as possible down through that triangle to the green area of lower risk. So I showed this diagram earlier, and there are a few examples here listed of the types of processes and documents that will be generated. So the activities you might have to produce a hazards register, for instance, an actions log, you would start by identifying your hazards. So a hazard identification exercise would generate that list of hazards. You would potentially further into the sort of design process look at the working environment and health risk assessment type of study or operability review, using operations experience to develop the design, and potentially, if necessary, human factors or a sort of qualified ergonomist could be used to look at control room design or other elements, and we'll come on to an example of that later for the boat landing. ALARP assessments can be produced for particular issues and specific issues. And on the right-hand side, bow tie analysis, this links very much back to the hazard register and the actions log, and leads to the next slide where we've listed out these processes, the hazard identification process. And so at the core of this approach is a fairly standard applicable risk assessment process. So you want to risk identification is, what could go wrong. The risk analysis part is how bad and how likely that might be. At which points you look to review detailed risk analysis for significant hazards. So you would identify what are significant hazards, what are the most, in terms of likelihood, for instance, and severity, and identify those significant hazards for more detailed analysis. And in this case, we're thinking about things like bow tie analysis, potentially as an efficient way of documenting the controls that are managing your risk. And then you evaluate the risk. So what is it acceptable, or do you have to go back and think further about the risk? And if it's acceptable, then progressing through to risk treatment, applying the risk treatments you've identified, and moving forwards into operation within the boundaries of those treatments and controls. So each of these components on wind farms often has different contractors or different contracts and different companies delivering them, perhaps for the overarching owner employing various different contractors for the onshore substation, the offshore substation, perhaps the wind turbine being a separate supplier, etc. And so there are different approaches to managing the risk through contracts, but the ALARP approach can be applied to each of the different components or the main components of the wind farm to make it manageable and to have consistency across your process. So you might separate the wind turbine and the wind turbine foundation if they're being supplied by different contractors. And ultimately it's an approach that's applicable to any and all of the areas of the project, which and the risks that they present. So to make it a more efficient process, one of the things we have looked at is to categorize risks as common risks that are known within the sort of offshore wind farm industry, where there's good practice guidance, for instance, around them. And we term those significant accident hazards. And we can look at to make sure that the higher risk areas are managed effectively or covered effectively by this process. And on the right hand side shows how these significant accident hazards fall into some generic groups: occupational risks, control of hazardous energy, fire, high pressure hazards, electricity, machinery, rotating equipment, structural integrity, so failure of equipment, and emergency response. And each of these areas you could envisage, and what we have done in the past is develop a bow tie where you look at the threats, the control measures to prevent that threat from becoming taking place, and the consequences of that event, and the control measures which mitigate the consequences or prevent the consequences from occurring. So you might end up with a bow tie for each of those significant accident hazards, and it's a good way of illustrating and presenting the control measures across your diverse assets on the wind farm in a clear and visible way during the design process, but carrying that through to operations and using those as training materials and making sure that everybody is aware of what the controls are and why they're important and what they're managing and against. So I'm going to just move through to this incline boat landing example, and as you can see from this diagram, we've got quite a tall structure, so you have working at height is a risk, but there are quite a lot of interacting elements going on here. So you have the vessel itself and hazards associated with that, which links into potentially structural failure. The vessel could impact the boat landing structure and cause damage to it, potentially, or you also have lifting activities. So, for example, just going to show you on the right-hand side, we have an example of an inclined boat landing here. At the top here is a davit crane, which is used for lifting operations. You have health and medical hazards. So over a 20-year career climbing these boat landings, that's a lot of ladder climbing, and it puts stresses and strains on joints and muscles, and there's also, so the final one is emergency response. So there's the potential for somebody to slip and fall, and on the inclined boat landing, for instance, an example might be, what if somebody fell here and ended up behind the ladder? How would that be solved? Is it possible to rescue somebody from behind a ladder? So these were concerns that were raised. So there are a number of uncertainties, and different stakeholders had reservations about incline boat landings, because partly most boat landings at the time were vertical and have been fitted to vertical monopiles, which is the sort of typical foundation design at the time that you see. The most efficient method of attaching a boat landing to a vertical monopile is a vertical boat landing. Ergo, when you have a sort of inclined leg, which in this case you had a leg that was inclined at an angle, the most efficient way of attaching it is by inclining the boat landing slightly. As you can see, the angle isn't very great, but it does have affects the performance. So we had to show that the performance wasn't either adversely affected or that any problems could be solved. So there's a gap in industry guidance, for instance, on this. It didn't rule out an inclined landing, acknowledged that they could be put in place, and there was at least one experience in the UK of a wind farm with inclined ladders. So there was possibility of learning lessons from there. But as you can see, there were a number of issues that could and were raised about operating these inclined landings. And so the ALARP process was to develop a study and to involve as many stakeholders as possible in that process. So we initiated a series of workshops, and we got everybody's opinions and presented the designs and got feedback on it, and went away and worked on those issues and concerns, using a number of strategies to actually determine what constituted an effective ALARP argument, essentially. And so what we came back with was that the inclined ladder was in fact an ergonomic solution. Climbing an inclined ladder is less fatiguing than a vertical ladder. And to support that and provide evidence, we employed an ergonomic specialist who did literature reviews and found research which showed the levels of hand force and foot force that were applied comparing different angles of ladders to vertical, and looked at reach of different heights operators, tall, short, to prove that the reach was not impaired and that they could step over onto the ladder adequately. And in fact, the worst case was stepping back from the ladder onto the vessel because of the twist and involved in undertaking that maneuver. And so it was possible to sort of demonstrate that those things were not impaired. The other issues were that the bumper landing and the gap between the bumper and the ladder were maintained at all times, and that indeed an operator who falls on an inclined ladder is less likely to fall into that gap. They would rather fall forwards and be able to rescue themselves or self-rescue, grab onto the ladder better. And equally, that going back to the human factor study, that it would be less likely for the person to fall in the first place. If they slipped, their weight would be thrown forwards onto the ladder rather than thrown onto their hands, where they have a sort of rather weaker grip. And these other systems were for the rest systems were demonstrated to work. Vessel performance was demonstrated from evidence from the other wind farm, and the emergency rescue performance was simulated at a rescue training centre by experts in working at height and rescue from height. So that document and that process allowed the design to move forwards with a boat landing, effectively, which was decided and agreed to be an inclined boat landing. But there were still concerns from operations that accessibility would be impaired potentially, that it wouldn't be as easy to get to and from or it wouldn't be possible to get onto the sites in different weather conditions. So once the wind farm was up and running, further study was carried out to demonstrate and to evaluate the performance of these boat landings in actual practice. And one of the things about ALARP and the precautionary principle is that you have to be prepared to be wrong. But in this case, it could have been sort of a cost incurred if there was less access, and also, but equally, the process had given us confidence that this was unlikely, and also that, in fact, it offered a safer solution than a vertical boat landing in this case, in our case, in the case of this project. So moving on from that particular example, there are other instances where you have differences of opinion and different stakeholders' opinions, and so this template here represents a process that we've used to sort of step through to apply those same core principles, but in a sort of rather narrower frame, in order to stimulate debate and to develop a consensus to allow these design decisions to be accepted and agreed and move forwards. And it contains the same sort of components. So it's risk-based. So it's got acceptance criteria. You have a bow tie diagram which clearly shows the controls and the layers of protection, and it widens out the options considered, because in the options considered section it gives you the opportunity to brainstorm a range of different solutions that are possible, offer arguments why they're a good or a bad thing and therefore should be rejected or accepted, and those, once the decision has been made, then operational conditions and further actions to be carried forwards can be highlighted and raised, and the whole issue can be moved forwards with an agreed position on ALARP. So in conclusion then, the ALARP design process that we used was suitable in this case for achieving SHE compliance with UK regulations, but equally is applicable for anywhere in the world. The process just facilitates and supports projects to understand what risks there are and how they're being managed. So the combinations of methods and techniques can be used, and these can be varied and trimmed down to suit requirements. They can also be, part of contractual agreements and bids for different parts of the facility, so they're built into the design process, or the client or the owner can equally specify and state some some of the control methods and techniques that they want to be used on the project. I mean, in this case, the inclined boat landing key decision process worked, and it was a complicated issue. It did demonstrate a risk reduction. Feedback from operators, from people actually climbing the ladders, the technicians, was that it was as good, or where a difference was stated, better than a vertical ladder. The deckhands and vessel captains also fed back, and again, either the system performed as well, or the vessel was as stable or more stable on the inclined landing than the vertical. And this was also backed up by data gathered from intelligent vendors and things like that. So it facilitated that process and allowed the project to move forwards on a very sticky and contentious issue. And as I touched on in the last slide, the process can be scaled down, and the techniques can be tailored to suit the problem that's being considered. Thank you for your time. I've just seen that it's 46 minutes into the talk, so I will stop talking here and move on to question and answers if anybody's got any questions. Not sure how I can see that.
Okay, Richard, thanks very much. Absolutely bob on time. Well done. I've got the questions in front of me. So we've got a couple of questions come in, but please, anybody else, if you've got any questions, please just type them into the Q&A function, because we've got a few minutes. So first question from Yanis, where he's asking, what about environmental tolerable risk? Perhaps mammals, underwater noise, bird striking. I think this was in the context of when you were first talking about the tolerability of risk, which of course you presented in the context of safety and individual risk to people.
Yes, no, it's really good point. There are risk criteria for environmental risks, environmental hazards that can be used. Very often, the issue of mammals and bird strikes were kind of outside of this process and were really dealt with by through the environmental assessment, environmental impact assessment, the environmental compliance type of processes. So the environmental impact statement would have looked at construction hazards like noise affecting mammals, through piling activities, and how those risks could be mitigated. And I mean, for those, I could see how you could adapt the process to those, so mammals and things like that. By you've identified the hazard, you identify controls. You could write a bow tie on mammal protection, but in the UK certainly there seems to be an established approach, really, which is enshrined in the regulations. So really that's why those things are dealt with through environmental impact assessments, environmental statements, and that sort of thing. And I guess people like the Environment Agency, SEPA, marine conservation groups and things like that are more familiar with that as a process than ALARP. But what it does do is where you have a hazard which may have a safety implication, it may not do. For instance, if you store, let's say you store diesel, you have a diesel generator, emergency diesel generator on your offshore substation, then if you get a loss of containment incident you could have envisaged diesel leaking to floor and to dripping through onto the sea, which would have an environmental impact. And I mean, it would also potentially have a safety impact as well, fire as well. But that environmental impact it is generally sort of something you would consider in this process. So your risk assessment, where you looked at consequences, you would have safety and health consequence criteria, and alongside that you have environmental consequence criteria from sort of high through to low, whatever. And through applying the matrix in the same way, you can apply the consequences and the likelihood of that incident, and put that environmental risk on in terms of acceptable high risk, medium risk, low risk, and how acceptable it is. So,
okay, yep.
So that's sort of would be my answer there.
Yep, thank you, Richard. We've got a question from Matthew, and I think this is probably coming from the context of the offshore structures are essentially unmanned, apart from when obviously people are visiting for maintenance or inspection activities.
Yep.
So question from Matthew, where would intentional vandalism sit, or terrorist threats?
Yeah, terrorist threats as well, yeah. Well, I mean, those are typically covered in DMV industry standards, which are typically what are applied in the UK anyway to so if you talk about an offshore substation, they would specify the requirements for a secure access. So they would have a mariner's cage where you could get to a certain point, so that for sort of life safety you can climb and seek shelter in the mariner's cage, but it's locked and you can't get to the equipment via that route. I mean, CCTV as well would be another way of detecting intrusion, and those sorts of measures would be sort of encapsulated within the standards.
Okay, thank you. A question from Liam, a really good question actually. Should a safety case regime be in place for offshore wind? The design safety process seems very similar to oil and gas operations.
Yeah, I mean it's not, and the sort of major accident hazards aren't the same really. So that's really the reason why the offshore regulations aren't applied. So in the UK, I mean, I don't know if you're aware, Liam, but I mean the UK regulatory regime, so work at heights, all of those sort of standard regulations, the provision and use of work equipment regulations and things, those are extended to offshore energy, including wind farm assets. But the offshore petroleum regulations, they do mention petroleum in the title and aren't. Now, whether they should or not, I think that, in my experience, if you apply those regulations, the work at height regulations, the electrical safety, regulations and all of those things, those really are addressing the hazards that the predominant hazards on these offshore installations. And so, provided that you follow the good practice, those electrical hazards, those work at height practices can be basically reduced to as low as really practicable. And so long as you have the difficulty is that you're 20 kilometers or 100 kilometers offshore, so you do need extra provision for emergency rescue, but provided your emergency arrangements are in place and you've got resources on hand, really those sorts of, you're addressing all of the hazards that exist on your offshore facilities, but and you don't really have a significant, even if you have some diesel on your thing, there's not really a major sort of explosion or fire risk. Well, I mean, there is, but I mean, it's not the same as an oil well or a gas, well, and including, the environmental risk is much more limited as well. So for those reasons, I think that there's a reason, my view, there's a reasonable argument. But I mean, what you can do is use this process and effectively produce a fit for purpose and suitable and sufficient, the documentation you produce, the bow ties, the forward actions and the procedures and standards that you would have in place are all things that form essentially an operational safety case. So it's a de facto operational safety case, even if it's not described as a safety case in any regulations.
Yeah, exactly. Just reinforce what you said there, really, Richard, that in the oil and gas sector, we have the potential for major accident hazards, particularly driven obviously by the hydrocarbons that are being processed. There's legislation that requires the formal documentation and submission of a safety case to demonstrate that risks have been reduced to ALARP, and you get your A-to-C assessment and subsequent inspections and so on associated with that. In the wind sector, I guess we've got probably might be viewed as a high hazard sector, perhaps rather than major accident hazard sector. But the process after that is exactly the same. It's a risk assessment based process. There will be HSE assessment and inspections, and therefore you're taking a fit for purpose approach. You just don't have to formally submit a safety case document to the regulator.
I mean, sorry, Steve. I mean, there is an equivalent onshore as well. Where you have a wind farm, an onshore wind farm, it has to comply with the UK regulatory regime under the Health and Safety at Work Act. But if you're a COMA after a control of major accident hazard operator, i.e., you have chemicals, hazardous chemicals, or toxic or flammable chemicals in inventories of a certain size, you have to submit a COMA safety report. But would it be sensible for an onshore wind farm to produce a safety report?
Yeah. Okay, great. Thank you very much, Richard. I thought that was a good example, actually, of a case study where perhaps the issue at first glance seemed to be relatively straightforward, but the issue with the stakeholders was that there was no experience of inclined ladders, therefore it was novel, therefore they automatically had a number of concerns, and it's the risk assessment and the ALARP process that helped to unravel all of those issues and come to a sort of evidence-based conclusion, and then that's actually unlocked the organization and allowed it to find a solution and for the design to proceed. So I thought it's a great example of applying a structured facilitated assessment process. So yeah, really good. Thanks, Richard. Okay, we need to wrap up now then. What we will do is make a recording available to everybody later this week. When you leave the webinar, you should automatically receive a survey in your browser. Only takes about 30 seconds to complete. Now, we're especially keen to hear any suggestions you may have on future topics, in particular for our next series, which we're planning for July, August time later this year. Now, if you've got any questions arising from what you've heard today, or you'd like any information on any of our services or training or whatever, you can simply email us. I think if Richard just advanced the slide, there's a slide that shows our inquiries email address. Earlier on, you'll see Richard actually had his own email address. I'm sure he'll be happy to receive any questions from you. Or alternatively, just go to our website, risktech.tuv.com, and there's plenty of forms on there. You can just fill in and fire them through to us. So thank you, Richard, once again. Thank
you.
you everyone for your attention. We're really grateful for you taking the time out of your busy schedules to listen in today. And that's it for this series. Hopefully we'll see you again in the summer. In the meantime, please stay safe and stay secure and enjoy the rest of your day. Goodbye.